Alright, today's video we're going to look at the Ampere-Maxwell Law and what it means. Here is the entire law written out mathematically. Ampere's law looks like this when an electric current, I or A, alright, so there's your I, right, is changing electric flux through a surface produces a circulating magnetic field around any path that bounds that surface. Electric currents and changes in electric fields are proportional to the magnetic field circulating about the areas where they accumulate. And that's what this equation helps us solve, and I'm going to break this down by the different parts. I'm going to go this part, then this, then this, then this on the preceding slides. So the first part is the induced magnetic field circulation, and that's here. The electric current or a changing electric flux through a surface produces a circulating magnetic field around any path that bounds that surface. So that's what this part of the equation solves. The current and the induced magnetic field follow the right-hand rule as shown here. So we use the right-hand rule to determine where the induced current is going to go in the magnetic field. The magnetic field circulation is calculated by doing a line integral of the dot product of B and dl. So here's our B and dl. dl is just an infinitely small differential length of the path on this circular enclosed path C. So that's what we're trying to solve with the induced magnetic field circulation portion. The permeability of free space is right here. The magnetic permeability determines a material's response to an applied magnetic field. Here's the permeability of free space, called vacuum permeability, and there's the units. This part, the enclosed electric current. Enclosed means that this current penetrates through any surface which is bounded by the closed path C. And you can see a couple of examples here. We must consider the direction of the electric current relative to the direction of magnetic field B's line integration. The right-hand rule that we saw previously determines whether a current is counted as positive or negative. And you can look back to see that. So let's look at this picture here. The electric current is considered as being enclosed since it penetrates any surface bounded by the closed path C, because the current goes through it. Now we look at the next picture here. This electric current is considered as not being enclosed because it doesn't penetrate one of the surfaces bounded by the closed path C. So in this case, the current bounces back out. So we don't consider that to be enclosed. Okay, the last part of the equation, the rate of change of electric flux. Okay, this is called the displacement of current. So this term right here is the electric flux analog of the changing magnetic flux term in Faraday's law of induction. Faraday's law of induction says that a changing magnetic flux through any surface induces a circulating electric field along a boundary path. This part was added by Maxwell into the original Ampere's equation. It says that a changing electric flux through a surface should induce a circulating magnetic field around a boundary of that surface. This term was added to solve the capacitor charging or discharging paradox that cannot be counted as an enclosed electric current. So let's just look at this picture here for this question. In the following figure, should IC be considered an enclosed current? And the answer is no, and here's why. Instead, we should count the electric field flux change between the plates of capacitor. So that's the Q and the negative Q. The electric flux change happens when the capacitor is charging or discharging. The electric flux change is calculated by integrating electric field E over the bulging surface which is bounded by the enclosed path C. Okay, so this is the path of our C here. And then take the direct derivative over time. And that's where all of this comes in to kind of explain this. I hope this made sense, and I hope you enjoyed this.